Welcome AP Statistics to Chapter 15. This is going to be a discussion on random variables. We're still talking about probability, but in a different and honestly a bit more complicated context. So buckle up, let's get to work. Let's talk about random variables. Makes sense. A random variable is a variable whose possible numerical values are the outcomes of a random event. Fair enough. We usually use X, that is a capital X, as a placeholder for a random variable itself. However, when we're talking about the variable's values, the values the variable can assume, we will usually use a lowercase x as a placeholder there. So when we talk about the variable itself, we will usually use capital X unless we have a better capital letter to deal with, and the values it can assume will use a lowercase letter. So a random variable whose possible outcomes can be listed is called a discrete random variable. So we would say if you can list the possible outcomes, if the possible outcomes are countable, that would be a discrete random variable. So you're saying that there are variables whose possible outcomes are not countable? Yes. We'll get to that. That's at the end of the section. Those are called continuous random variables. So for example, the random variable $value X could assume the values 1 for a $1 bill, 2 for a $2 bill, they're out of circulation, but you can find them if you look carefully, 5, 10, 20, 50, and 100. A continuous random variable is a random variable whose possible outcomes cannot be listed, which means all real numbers on a certain interval are possible outcomes. So for example, the random variable top speed of car X could assume any value from 0, you have a car with a dead battery, car that's out of gas, take your pick, to 316 miles an hour, which as of 2020, past then, at the point at which you're watching the video, there could be a new fastest car. But as of 2020, the SSC Tuatara, which is pictured up here, is the fastest car on the market for the road, the fastest roadworthy car on the market. We're not talking about like supercars that they take out to the desert and they go as fast as they can in a straight line and see if they can make a sonic boom. We're not talking about those kind of cars. So there you go. That would be an example of a continuous random variable. Any value from 0 to 316 miles an hour approximately is a possible output for that random variable. So probability models, all right? This is an example of a probability distribution, or what our book calls a probability model. A probability model shows all possible values of a random variable alongside their associated probabilities. So the probability model to the right depicts the payout possibilities of an insurance company that they would need to consider for their death and disability policy, right? So the payout possibilities for the death and disability policy. In a given year, an actuary with a penchant for contrived numbers says there is a 1 in 1,000 chance of an individual dying, 2 out of 1,000 chance of them becoming permanently disabled, and thus a 997 out of 1,000 chance that neither will happen and they can go on happily with their lives. The company pays out $10,000 if the individual dies to whomever is in the will, $5,000 for permanent disability, and 0 if life is fine and dandy. And that is expressed here in the table. We have the 3 levels of payout and the likelihoods that the insurance company will need to make those payouts. And now we get to talk about something called expected value, which once we define it is going to sound extremely familiar. The expected value of a random variable denoted E of X, or sometimes just, wait a second, that's mu. That's the population mean. The mean of the population, or the mean value, and the expected value are the same thing. We just see expected value in this particular context more than the mean, but the mean and the expected value are interchangeable. And that is the predicted value for the variable, considering all possibilities and all likelihoods of those possibilities. So for example, the expected value for the death and disability policy is the amount the company can expect, makes sense, to pay out per person per year. Now, does that mean that each person's going to get the same amount of payout? No. It would be really nice if no one had to get their payout and they were living fine and dandy. Hopefully not everyone inherits a disability, and hopefully not everyone dies. So we're not expecting the same payout for everybody, but for each individual, they're going to be in one of these three categories. So per person, how much can the company expect to pay out per year? That is a question of expectation. So we compute the expected value by multiplying each value of the variable by its respective probability and summing those products. So we say, for example, let's talk about the death outcome, rather morbid, but we got to do it. 10,000 is my outcome, and the odds of that happening are 1 in 1,000. So I do 10,000 times 1 in 1,000. And then I would add to that 500 times 2 in 1,000 and 0 times 997 out of 1,000. And if I add all those together, I would get my expected value for the payout. So the expected value for the payout of the insurance company is, as I have said, we make this whole string of terms right here, and that evens out to $20 per policy holder. You may think to yourself, wait, Mr. DeClerico, 10,000, 5,000, 0, I don't see a 20 anywhere. Why is that my expectation? Well, most people aren't going to need a payout at all. A very small number of people are going to need 5,000, and an even smaller number of people are going to need 10,000. So on average, each person is going to be receiving, and again, averages here, we're not considering that everyone's going to be scot-free or everyone's going to be disabled or dead. We got to consider everybody and all of their outcomes. Per person, you got to account for $20 per policyholder, okay? Most people are going to be just fine, but there are going to be enough people in this category, if there are a lot of people in this insurance plan, that you got to account for $20 per policyholder. So even though no one's getting $20, that is still the expected value. And for every policyholder, you are accounting for $20 on average. And when it comes to the cost of this policy, that becomes really important because this company has to not only meet the $20 per person, but exceed it enough to pay all of the workers for this insurance company. So this is going to help determine, that is, the cost of the insurance. So let's do some problems with expectation. On Valentine's Day, the Quiet Nook restaurant offers a Lucky Lovers special that could save couples money on their romantic dinners. When the waiter brings the check, he also brings the 4 aces from a deck of cards. He'll shuffle them and lay them out face down on the table. The couple will then get to turn one card over. If it's a black ace, they owe the full amount. But if it's the ace of hearts, Valentine's Day, the waiter will give them a $20 Lucky Lovers discount. Ooh, that's nice. If they first turn over the ace of diamonds, hey, at least it's red, then they get to turn over one of the remaining cards, earning a $10 discount for finding the ace of hearts this time. So notice there are 2 ways you can get discounts. You can get the $20 by choosing the ace of hearts, or you can get $10 if they get the ace of diamonds followed by the ace of hearts. Okay? And if you don't get either of those, you don't get anything. So based on a probability model for the size of the Lucky Lovers discount at the restaurant that the restaurant's going to award, what is the expected discount for the couple? We see this word expected, and we should think expected value. We're trying to find a mean here. So Making the table for this takes a little bit of concentration, so I'm going to show you what the table would look like, what the probability model would look like. So here's a probability model you could use. We have 3 different outcomes. You get an ace of hearts on the first draw, you get an ace of diamonds followed by an ace of hearts, and an ace of clubs or ace of spades on the first draw. Those are the only 3 things that can happen in this scenario. Ace of hearts on the first draw, you get a lot of money off, and it's easy to compute. There are 4 aces, you're choosing one, that's a 1 in 4 chance. The ace of diamonds and then the ace of hearts. This one is a little bit more tricky. The discount is $10, that's the easy part. But we need to think, what are the odds of first picking the ace of diamonds and then picking the ace of hearts, knowing that we no longer have an ace of diamonds in the set of cards to choose from. So there's a 1 in 4 chance of choosing the ace of diamonds, and then we need to multiply by a 1 in 3 chance of choosing the ace of hearts, given that there's no ace of diamonds, okay? So the 1 in 4 would be choosing the ace of diamonds times, because this is an and scenario, 1 in 3, because then there are 3 cards in the waiter's hand, and you want to choose one of them. So it's 1 out of 4 times 1 out of 3 is equal to 1 out of 12, interestingly enough. So these 2 values, the 1 out of 4 and the 1 out of 12 we just computed, are going to help us find the probability of our third scenario, which is everything else that could happen. The ace of clubs or the ace of spades on the first draw. Now, you might look at that and think, wait a second, that's a 50-50. It's not. It's not, because this is the only circumstance other than these 2 circumstances. So if I were to do 100% minus 1/4 minus 1/12, then I would get 1 minus the sum of the other probabilities is actually equal to 2/3. This is why it's so important for us to make a probability distribution, because if we just go into this problem finding the expected value and we're not careful about it, we might come up with a very wrong expectation and get the wrong idea about what this restaurant is offering. So now that we've done that, that is by far the trickiest part. Expectation from here is easy peasy. The expectation for our random variable x being the savings that we will get from the Lucky Lovers discount, that would be $20 times 1 out of 4 plus $10 times 1 out of 12 plus $0 times 2 out of 3, and that's going to be $5.83, which again, there's no way we can save $5.83, right? We can save $20 or $10 or nothing at all. But per table, your savings are going to be $5.83 on average, which, and if you ever go to a restaurant on Valentine's Day, you'll realize this savings right here might need to be compensated in some way, which means the food and drink are going to be a bit more expensive. I've warned you ahead of time. One more example. So one of the authors of the textbook we're going through took his minivan in for repair because the air conditioner was cutting out intermittently. The mechanic identified the problem as dirt in a control unit. He said about 75% of the time, drawing down and then recharging the coolant a couple of times cleans up the problem, and that costs only $60. If that fails, however, then the control unit must be replaced, and an additional cost of $100 for parts and $40 per labor would be tacked on. So 3 parts of this. We want to define the random variable and construct a probability model for this situation. And then what is the expected value of the cost for this repair, and what does that mean in this context? Okay, so let's consider what the possibilities are. Well, 75% of the time you draw down and recharge the coolant a couple of times, and that deals with the problem. That's only $60. Otherwise, the other possibility is that you have $60 for trying the way that didn't work, plus $100 for parts and $40 for labor. So see if you can come up with a probability model, compute the expected value, and determine what that means in context. Okay, I'll assume we're ready to continue. Here we go. So here is our probability model. We have two different outcomes. We have the chance that the recharging works and the chance that it doesn't. We need to replace the control unit. $60 for the recharging and $200 for the recharging that didn't work, plus $100 for parts and $40 for labor. The recharging is going to work 75% of the time, and 25% of the time replacing the control unit is going to be what's best. So again, solutions from the textbook. We have $60 times 75%. That's going to be considering what the cost would be for recharging and the odds that works, plus $200 times 25%, the more expensive route we might need to take, and the odds we need to take that route. Either this or that is going to be the route we need to take. That's an or statement, so we use addition rules, and so we would get $95. All right, these are mutually exclusive events. We either do that or that. We don't do both at the same time. So that would be $95 is going to be our expected value. So in context, that means car owners with this problem will spend an average of $95 to get it fixed. All right. So 75% of the time it's going to be cheaper, 25% of the time it's going to be a lot more expensive, but we can expect $95 on average every time that this kind of thing would happen. So there you go, expected value to compute the cost of fixing a silly thing wrong with a car.